make your voice a bit louder. I mean, I think the mic is turned down.
Okay. So if there are no questions, I'll begin. So let me recall where we arrived last time. So we started with a system of three kinds of objects. So let me remind you. So we had three systems. The first one was free electrons and protons. And the number density of these is what we call Ne, which is also the same as N. Then we had NL states for N greater than or equal to 2 in thermal equilibrium. So which basically means that we took NNL to be given by 12 plus 1 N2S times 2 minus. So all the NNLs are determined in terms of the 2S density. In particular, the total number density is sum over NL, which is N2S and sum over NL, 12 plus 1 times e to the minus E2S minus. And this quantity we called F of T. And the third system was one states with number density N1S. We started by setting up the differential equation that describes the possible transition between these three systems, keeping up the total number fixed. And in that, we will make the approximation that there is no transition between 1 and 3, because if there is a transition between 1 and 3, it produces highly energetic photons, which basically eventually kicks out a 1 state all the way to free electrons. Okay, that it will happen in stages because it may kick the 1 state into a high NL state, and then thermal photons will kick it out to the free electrons. So we'll only consider, so that balances out. So we'll only consider transition between 1 and 2 and between 2 and 3. Are there questions on this? So first we start with, okay, actually I should say total number. So total number density is Ne plus NNL N2S F of T plus N1S. And this should be equal to the baryon density NP times 0.73. That's the total number of protons, free and bound. And this in turn is given by 3 omega b by g times 1 over lambda cube. And this 1 over lambda cube you can also write as T over T. So this is something which is known. So only 2 of the 3 really are independent because the total has to add up to n. So we first wrote down the equation for d dt of any lambda cube. And we said that this should be given by sum of two terms. We have the difference between two terms. First one tells us how fast this is depleted. And that was given by n, a times np, n lambda cube. Because it's proportional to any lambda cube, because of course it's you always calculate probability per unit electron. Okay, what is the probability that this will get bound to the NL system? And then it depends on NP because it depends on how many protons are there, because electron has to find a proton and combine to produce this bound system. And then there is an opposite reaction, P, which tells us the rate at which this bound system in the NL state gets converted to the free electron and proton by thermal photons. So that's given by P times N2S. And this, as we saw, that this includes transition from all states, right? So B is just a coefficient, but it represents the transition from the total transition rate from any of the NL states to the electrons. And then we also gave the expression for A and B. So A was sigma times B, where this is the capture cross section. So this is known from experiment. And you can also try to calculate it theoretically and theory. And then B is determined by using detailed balance. Of course, this is also you could calculate in principle starting from the microscopic theory. But we use detailed balance and the equilibrium density to conclude that B must be related to A by So as far as this reaction is concerned, everything is known. We know A and B. So you can, in principle, just put it on a computer and try to evolve this. So now we'll turn to the transition between 2 and 3, the second and third system. So we are now talking about, so let me maybe draw a figure. So here is free electron. Then this is NL states, okay, which of course has a band. But as you saw, that it's predominantly only 2s and 2p states, because all the higher NL states are very sparsely populated, right? So even though we are talking about NL states for any NL, the main players here are the 2s and 2p states. Okay, and that's what you'll be using. And then there is this 1s. So we can write, let me write the equation, then we will explain the term. So dBT of N1S lambda cube. So first, let me write the production. Okay, so I'll try to explain these various terms. So gamma 2s is the transition rate US. Gamma 2p is the transition rate for 2p. P will be the probability. Okay. Now you see that I have only included 2s and 2p states because, as I said, all the higher NL states are very sparsely populated and they don't really play too much role in this. Okay, so this is what we have here. And this factor of 3 is because there are, this is L equal to 1, so there are 3 states. Okay, so the total number of 2p states is 3 times N2s. That's why there's factor of 3. So P is the probability that photon produced in 2p to 2s, 2p to 1s transition. These are known as the Lyman alpha photons. That this escapes without causing this. So this, let me explain. As we saw that from free electrons to 1s is not possible because whatever photon is produced will eventually kick out a 1s electron to free electrons, right? So that process gets balanced out. Now a similar phenomenon may occur also for the 2p electrons. Okay, for the 2p states, because once 2s doesn't have this problem. Okay, because as we saw, the 2s goes to, let me remind you these transitions, 2s goes to 1s plus 2 gammas. So each of these gammas have less energy compared to the one that is needed to excite a 1s to 2s. But 2p goes to 1s plus gamma. So this gamma has just enough energy to excite an 1s to 2p. So we have to, and if that happens, then effectively this transition is not of much use, right? Because whatever that part, that if the probability, for example, is not 1, right, then that means there is a small probability, there is some probability that some of the photons will excite the 2p back to 2s. Sorry, will excite the 1s back to 2p. So this factor of p basically takes that into account. So this counts the fraction of the Lyman alpha photons that are produced in this transition that do not cause the 2s to go back to 2p, right? And that's what we mean by saying that it escapes without causing 1s to 2p transition. And E is the reverse rate, which we will see how to calculate. So this E is 1s to 2p, 1s to 2p transition. Let me write that down. minus 2s, 2p. Are there questions?
Hello. Hello, Ashok.
Let me
Can you hear me?
proceed.
Yeah, I have one doubt. When we write this uh, gamma 2p, this 2p to 1s transition, you said this 3 is coming from the 2l plus 1 we are writing, right?
So we'll calculate p later. Okay? So let me say this. So we'll
Okay.
calculate
So,
p later.
so this p will have that exponential suppression contribution.
Oh, yeah. Another thing I wanted to point out here is that these rates, so these, as I said, you can in principle calculate from microscopic theory, right? Gamma 2s, that you just take a 2s photon and you can in principle either do an experiment to see what is the lifetime, right? And from that you can calculate gamma 2s, or you can take a 2p state and find its lifetime to calculate gamma 2p. But these decays here are happening in a thermal bath. And because it's happening in a thermal bath, there will be an additional factor. If you recall, for neutrino, for example, that we had an additional factor which suppresses the production if there are already neutrinos present because of the Pauli exclusion, right? Because if, for example, so you have to multiply this by the probability that the particular neutrino state is not occupied. Now, the same thing you have to do here, right, for the photons, because you have to make sure that whatever photon is produced, that state, well, in this case, photons are bosons, so you don't ask for it's not being occupied, but if it is occupied, then the probability gets enhanced. It's basically the same difference between plus and minus. So whatever formula you use, for example, for the neutrinos, you have to basically switch pluses to minuses, and you will see that the presence of a photon in the final state actually enhances the probability of producing such photon. So in principle, you should, while calculating this, you should also multiply this by those factors. But what happens here is that the energies of those photons are so high compared to the temperature that we are talking about, okay, like 3000 K, that those factors are extremely small, right? The probability that a photon is occupied in the final state is extremely tiny, and so those factors are so small, but they don't really affect this calculation. But we should keep in mind that if you are doing a completely rigorous calculation, then those factors should be present. That when the decay is happening in a thermal bath, we have to take into account the fact that the photons may be present in the thermal bath, and that will change the decay. But in this case, as I said, it's counterintuitive because you don't have Pauli exclusion. It's the opposite. That if there is a photon already in the final state, it actually becomes more probable for the photon to be emitted in that state. But we will not use this in our analysis. I can see some in the chat. No, I'm not able to hear you. Yes, so can you unmute and okay, just 1 minute. Maybe I have a problem. Okay, yeah. Can you speak now?
Hello, hello. Can you hear us now?
Yes, I can hear you now. Okay. Were there questions that I didn't hear?
Yeah, actually, I had one question. Hi, Ashok.
Yes.
Yeah. So when we write this 2p to 1s transitions, we write some 3 and 2s, right? This 3 is coming from 2l plus 1.
Exactly. Yeah.
And there is an extra exponential binding energy difference divided by T in that formula, right?
In the 2s
When we write
when
we write NL in terms of N2s, N2s.
Yeah. So the point is 2L and 2S, sorry, 2P and 2S have the same energy, right? That energy you are ignoring, that energy difference.
Okay, the degeneracies are ignored.
Yeah, because to first approximation, 2s and 2p are degenerate.
Okay. Okay. Fine.
Otherwise, you are right that you have to include that small difference in this, right? That will go in here.
Okay.
Thank you. Yeah. Are there other questions? Okay. Okay. So as I said, this P is something that has to be calculated. The transition probability, and this we will be doing later, hopefully in this lecture itself. But first, let me try to say what this E is. Right? E is the reverse rate, but how to calculate E? So how to calculate E is what you focus on. E. Again, we could in principle start with it from microscopic physics. Can use microscopic physics. But we'll use detailed balance. So let's suppose that you have thermal equilibrium. You have thermal equilibrium. The thermal equilibrium means no expansion. And Ne is very small. Okay, this is a hypothetical case. Right? Imagine that the density of electrons was so small that the fact that we produce some high energy photon doesn't affect the thermal bond. Okay, so that will be the case for thermal equilibrium because the photons are providing thermal bath and we don't want the bath to be disturbed. So in this case, we can use detailed balance. Right? The total transition rate from one system to other must balance the transition rate in the reverse direction. So the detailed balance in this case will tell us ddt of n1 is lambda cube equals 0. Okay, lambda is 0, lambda is constant anyway. And this will tell us that gamma 2s plus 3 gamma 2p. Okay, I should have said so. In this case, p is also 1. Let me go back to various conditions. Okay, once you say thermal photon particle any, this means that the p is basically 1. Okay, because you are taking the limit of the density of 3 electrons and 1s, etc., all very small. So that once you produce this photon in the transition, okay, it basically never excites another 1s. Okay, all this is being done by the thermal photons, right? Thermal photons may be exciting 1s, but the fact that there is a small probability that the Lyman alpha that is produced from 2p to 1s transition excites a 1s back is extremely tiny, right? Because you are taking the limit where the density of such objects are going to 0. So P I have set equal to 1. Okay, no back reaction. And so this times N2s will be equal to E0 times N1s. Okay, I have use the subscript E naught because as you will see that E is not the same as E naught. Okay, for reason we'll see in a few minutes. So now you use the fact that in equilibrium, N2S is N1S times e to the minus E1S minus E2S T. You conclude that E0 is gamma 2S plus 3 gamma 2T. Okay, is this clear? Are there questions on this?
Why we used epsilon 0 here? E0?
Yes, I'll explain in a minute, right? Because actually E will be different from E0. Okay, I'll explain why this is different. Okay, this would be the case. This would be the transition rate back from 1s to 2p in thermal equilibrium. Right? So the question is whether that equilibrium formula we can use for the system that we have. Is this clear? Yeah. Yes,
Can
go
you
ahead.
please again explain the hypothetical setup we are having to derive E naught?
Yeah. So hypothetical setup is that you have perfect thermal equilibrium where the density of electrons and protons is so small that there is no back reaction back on the thermal photons, right? So that you can always continue to use the thermal distribution formula to count the number of photons of a given energy.
Okay.
So that these Lyman alpha photons that are produced from 2p to 1s, they are so tiny compared to the thermal photons that are present that their presence is irrelevant, right? That's the hypothetical situation. Right? Because that's where you have thermal equilibrium, right? Because in thermal equilibrium, we assume that we have a system in contact with a reservoir. The reservoir in this case is the photon, thermal gas of photons, and the system is the electron-proton system, right? Electron-proton hydrogen atom system. And in order that it doesn't affect back the reservoir, we have to make sure that the density is going to 0. Right? In that limit, we can use the thermal equilibrium formula.
Which density is going to 0?
The density of electron, proton, and hydrogen atoms.
So that the
we
back
have
reaction on the photonic gas is insignificant.
Exactly. So the effect, see, we have 1 in 10 to the 10, right? So we had said that because of this low density, mostly it doesn't affect the photon gas, except in the case when there are very high energetic photons involved. There, it could in principle affect the photon gas because the number of photons of such high energy can be small, right? And that's the reason why we have to do more than use equilibrium physics. In this case, you see that what is the kind of energy, photon energy that you're talking, right? We're talking about photon energies of order. So we are talking about energies of order P1s minus P2p. P2p and 2s are the same. And this is like 3/4 of 13.6 electron. We had seen earlier that if we take e to the minus 13.6 over T, right, which is 3000 Kelvin, that's much smaller than 10 to the minus 10. And that's the reason why we cannot ignore the presence of the photons that are produced by these transitions, right? Because their number is comparable. Their number is of order of the number density of electrons and protons, while this number of thermal photons of the same energy is extremely tiny. Now we have a slightly better situation because instead of having 13.6 here, we have 3/4 times 13.6, but it's still very, very small. It's much smaller than 1 in 10 to the 10, and that's why we have to. That's why you cannot use equilibrium formula, but you can use equilibrium physics to figure out what the transition rate is, right? And that's what we are doing. Is this clear? So the equilibrium is achieved in the limit when the number density of electrons and protons is much smaller than this. When the Ne over N gamma will be much smaller than this number, right? And that is not the situation in cosmology at that time, but we are using this hypothetical system to figure out what the transition rate is by using detailed balance. Okay, otherwise, as I said, you could do it from microscopic physics directly. Okay, using crossing symmetry, the 1s to 2s will have some relation to this, right? The 2s to 1s or 2p to 1s transition. And then you have to use the thermal distribution formula, convolute it, and then calculate it not directly from microscopic physics. Now, why is E different from E? So E naught is the transition rate from 1s back to 2p, 2s, assuming that it is states. Now, this is not true because of two reasons, right? This is not true due to two reasons. The first reason is that the thermal bath, the background, has gamma from previous 2p2 the ones that are produced from 2s to 1s are not relevant because those photons cannot do anything to the 2s or 1s states. Okay, but to 2p to 1s, of course, you have to take into account. But this effect, right? So why is this important? Because those gammas they are not part of the thermal bath, but they could keep that 1s back to 2. But this has already been taken into account as already been taken into account in P. The fact that the sum of the photons that are produced from 2p to 1s can kick the 1s back to 2p. That is the reason why we use this factor P in the first place. If you see this factor of P, go back one more step. This factor of P is precisely taking into account that fact that some of the photons that are produced from 2p to 1s can kick the 1s back to 2. So we don't have to worry about those photons anymore. So let's not worry about those. The second point is the following. That some of the thermal photons of energy of order omega So this means that the actual number of thermal photons, in the path with energy of order 1 V1 is less than what will be the thermal. Again, if the thermal bath was much, if the thermal bath had the number of photons in the thermal bath was much larger than the number density of electrons and protons and hydrogen atoms, then it did matter, right? Because it is true that some of the photons might have been absorbed, but that will be a very tiny effect compared to the number of photons that we already have. But in this case, as you saw, the expected number of photons in thermal bath of this energy V1s minus V2p or V1s minus V2s is much smaller than the number of hydrogen atoms or the electrons that we have in the system. Which means that even if a small fraction of the 1s hasn't gotten excited to 2p by absorbing thermal photons, the number of thermal photons would have gotten depleted. So the actual number of thermal photons that are present at any given time is less than what a thermal ensemble will give, right? Because thermal ensemble will just use the black body formula, but some of those photons may have already gotten absorbed by a previous 1s to 2p transition. Is this clear? So at any time, we only have a fraction, let me call this p bar, of the expected number and so this factor p bar also has to be put in this formula, and that will count the difference between E and E naught. Right? So E naught was this factor, right? And you can see from here that 2s will be the reverse rate from 1s to 2s, and this will be the reverse rate from 1s to 2p. But this, in order for this to happen, right, we are essentially using the thermal photons of that energy, and those actual number of thermal photons that are available is less than what a thermal bath would give. So that P bar will essentially come in here. So let me write the formula for E. So E will be given by gamma 2s plus 3 P bar. Are there questions? Okay, with this, let me now set up the equations. So we have d dt of any lambda cube equal to a n squared lambda cube plus 3 cube and d dt is where E is given by this. So you see that there is a P here and the P bar here, right? They are similar, but they have slightly different roles. This P, again, let me remind you, is the probability that a Lyman alpha photon that is produced from 2p to 2s transition doesn't excite back from 2p to 1s transition, doesn't excite back the 1s to 2p. Whereas this P bar is the fraction of thermal photons that survive, thermal photons of energy of order of the Lyman alpha photon that survives the capture by 1s to 2. Okay, so now we use the fact that we have this other relation, the dV.
Ashok, hello.
Yes.
Can I just explain this P bar one second? P bar is
bar,
the
yes. Okay, so P bar is coming because we said that the E naught was calculated assuming thermal equilibrium. This E naught formula that we have, this is calculated using thermal equilibrium, assuming that the system is in thermal equilibrium, right? Which assumes something about how many, what fraction. So which part of thermal formula that are relevant here, right? The part of thermal formula that is relevant here is that what is the number density of photons which have energy to excite it 1s to 2, right? And that's why you are seeing this the factor over here, B1s minus B2s, right? Because it has to excite the 1s back to 2. So if we really had a thermal bath, then this will be the correct form. But the actual environment that the system is subject to, right, has less number of photons of this energy, like of energy B1s minus B2s, than what a thermal distribution will predict, because some of those photons would have already been gotten absorbed by 1s to get excited 2. And because the number of 1s atoms is large compared to the number of thermal photons that you have of this energy, this will have a significant impact on thermal environment. Because once you absorb, say, some photons from the thermal environment to excite 1s to 2p, then you're losing those photons. And then later on, the 1s states that are present do not have those many photons to interact. And that is this factor of P bar. So what we are saying is that in order to actually calculate the rate, it's not this, but it's gamma Ts plus 3 P bar times gamma 2P. Because that 1s to 2p transition, which is being captured by this, is affected by the depletion of the thermal. 1s to 2s is not affected by this because 1s to 2s goes by absorbing 2 photons, and so it's not depleted that much. Okay, it's the 1s to 2p that requires 1 photon of very high energy, and that is depleted, and that's why the P bar is coming.
okay, yeah, good.
Any other question?
Hello.
Yes.
So once this depletion happens, I mean, shouldn't we think of it as kind of deviation from equilibrium? We can no longer consider that to be equilibrium, right?
Yes, indeed. So that's why this is not the equilibrium formula. The formula for E that we are using, right, is not the formula that we have in equilibrium, but the factor of P bar is precisely capturing the fact that it's not in equilibrium. So if it was in equilibrium, it would have been gamma 2s plus 3 gamma 2, right? That's what we derived using the detail balance.
Okay.
So P bar is essentially accounting for the fact that you are not in equilibrium. The actual number of photons is less than what equilibrium will predict.
Okay. Okay.
Yeah.
Yeah. So there is no mechanism of let's say the number of photons in that particular frequency mode is getting depleted. I mean, there's no other mechanism apart from this Lyman mode mechanism that will kind of fill up those modes again.
No, because the photons have gone out of thermal equilibrium, right? As we saw.
Okay.
So it's not thermal. It's not thermalizing.
Yeah, okay. It looks like a thermal equilibrium, but it's not completely thermal. I mean,
exactly.
So I mean, yeah. So if there had been some other species with which the photon had been in thermal equilibrium, we need not have introduced a p bar, right?
Exactly. Yeah. Because then
Yeah.
by strongly interacting with that species, it will get distributed anyway.
Yeah.
Right. So you don't have to worry about this p bar being different from p.
Okay.
Here you have to worry about it because once the photon gets depleted, right?
Yeah.
You don't replace it by thermal process. So there are two things. Of course, you replenish it by the 2p to 1s transition, but that is part of p, right? That you have taken into account.
Yeah.
That's
I
why
mean, it seems that this is the only mechanism that can affect the population in those frequency modes, right?
exactly. In those
So-
frequency modes, you either emit one of those from 2p to 1s transition, or you absorb one of those.
Okay.
So those are the only two mechanisms that can affect the density of photons in that region. Right? And if this number had been small compared to the thermal contribution, then you didn't have to worry about this. But the point is that these numbers are not small compared to the expected number of thermal photons of that energy. Okay, is this clear?
Sir, can you explain once why P is not 1? P.
Why P is not 1?
Yeah.
But
Just
we'll
explain.
calculate P. Yeah, we'll calculate P, right? And we'll see that, okay, the reason we'll say, okay, the physics of why P is not 1 is because once you produce this Lyman alpha photon, right? Then it can lose energy. It can lose energy. I mean, primarily in this case, it happens because it's the universe is expanding. So it gets redshifted away. So if it can excite the 1s to 2p back by redshift, okay, maybe I should have said the other, yeah, so this, yeah. If, okay, p equal to 1 means what? That once you have produced from 2p to 1s, right? Once you have made the transition from 2p to 1s, you produce a photon, and p is equal to 1 means that that photon never excites at 2s back to 2, or back 1s back to 2, right?
Right.
But that may happen, right? That photon that you produce from 2p to 1s transition, that may kick back some of the 1s to 2p. Right? So then effectively you are not gaining anything, right? Because you are not gaining the number of 1s states. That's why p is not 1.
So because so P is basically is like a fraction of photons which are available. Is it so?
No. That is p bar. See, there are two different things. One is that you make a transition from, let me draw this figure, that you have, this is the 2p and 1s. So you make a transition from 2p to 1s that produces a photon. If that photon kicks another 1s and brings it back to 2p, then effectively that transition as if the transition didn't happen. So even though there is a rate gamma 2p for going from 2p to 1s, the actual rate of transition from 2p to 1s is not gamma 2p, but gamma 2p times p, because where p is basically the fraction of photons that actually causes this transition, right?
Okay.
If all the
so
photons
is it like
that are produced from 2p to 1s had escaped to infinity without exciting 1s, then it would have been gamma 2.
so it's like effective transition from 2p to 1s?
Yes, exactly. So p is like the effective transition rate from 2p to 1s. See, if there is a single isolated 2p, right, then you can calculate the 2p to 1s rate. That photon goes somewhere else, right? It goes up to infinity. It doesn't excite 1s back to 2. But here you're talking about a gas, right, which has many 1s states. In that case, if you make a transition from 2p to 1s, right, one photon is produced, and there is a finite probability that that photon will kick another 1s back to 2. That probability is what we're calling 1 minus. So p is the probability that doesn't happen.
Okay.
Is that clear? So that is for P, and P bar is a similar thing, but now we are talking about the thermal photons. That probability that the thermal photon density has gotten depleted compared to what the black body spectrum will predict. Right? If the black body spectrum predicts something, then the actual number, the density of thermal photons is P bar times that, because some of those black body spectrum, photons from the black body spectrum have already excited 1s to 2. Is this point clear?
Yes, sir. Yeah.
Okay. Any other question? Okay, so now let me add the other equation, NB times 0.73 times lambda cube. This is 0. This is a baryon density. This, let me remind you, was, well, this is the total number of P plus bound products, right? In H. The total number. Electrons. P and bound in H. Helium we are in. So we now define two things. The ratios. X. So X will define to be NE over 0.73 NB. This whole thing is that. Because the 0.73 already takes into account the fact that you need this 0.73 to take into account the fact that you have to only talk about the hydrogen atoms and not helium. Anyway, so you define X as NE over 0.73 NB and Y as N1S over 0.73 NB. And then this one, N2S, 1 minus X minus Y. Would be N2S times F of T over 0.73. Remember that NE plus N1S plus N2S times Ft should be equal to 0.73 NB. Okay, so that's why this ratio is 1 minus X minus Y. So using this, what we will do is that we will rewrite these equations in terms of X and Y. Okay, the fraction of electrons that are there as free out of the total number of electrons and the fraction of electrons that are there as 1s out of the total number of electrons. And then, of course, the difference must be in the NL states for n greater than equal to, right? And that's this equation for 1 minus X. So the idea is that we will take this NE lambda cube and divide by this. NE times 0.73 times lambda cube. Because ddt of this is equal to 0 anyway, we can always divide, take this in the denominator inside this time derivatives and similarly inside this time derivative. And that will give you equation for dx dt and dy dt. Right? And so we'll now rewrite these equations in terms of dx dt and dy. So you get dx dt as ax square times 0.73 NB. So we have a formula for this. So minus b times 1 6 minus 1 over 8. Okay, you see that on this side you had n2s, you have to divide n2s by this number. And that, according to this formula, is 1 minus X minus Y divided by F of T. Okay, f of t again is a known function, right? So everything here is known except the p and p bar, which you have to worry about. Okay, so this is dx dt, and then we have dy dt. Okay, in this equation, everything is known. In the later equation, you have to worry about t. So let me write the formula for dy dt. So it's gamma 2s plus 3 gamma 2t. So these two are the equations that you want to evolve numerically. Okay, and solve for. And the initial condition you can put many different things. For example, you could start with x equal to 1. At high temperature, you could start with x equal to 1 and y equal to 0, because everything will be free electrons anyway. Or at high temperature, you can try to use thermal formula. Okay, it doesn't really matter, because the time evolution will basically bring you back to whatever it was supposed to be. Okay. So then what remains is to calculate P and P bar.
Ashok, I have a doubt.
Yes.
In this, why there are no derivatives of lambda?
Oh, because if you look at this formula, ddt of this is 0, right? And we divide it by this whole thing. See,
Okay.
this is 0 because the baryon density is, the total density is going off as 1 over lambda cube. Right? So because we divided by this, right, there's no extra term coming from here.
Okay.
And so basically what happened, lambda cube got cancelled. Right? And you could write down directly the evolution equation for the fractions.
Yeah.
Okay, any other question? Okay, so the main task is to calculate P and P bar. Okay, and this is what I'll try to explain in whatever time we have. Okay, so let's introduce some quantities. So T omega, let's suppose that this is the probability that a 2p to 1s transition produces a photon But the first question one might ask is that why isn't this the energy? Just the frequency of the Lyman, the energy of the Lyman alpha photon is B1s minus B2. Typically, if you have a transition from a state of energy minus B1, energy minus B2 to energy minus B1s, the photon that you emit should be of this energy, right? That's by energy. The reason that it's not exactly this, okay, but of course it should be approximately this. So P omega should be peaked around omega alpha. Is that 2p is unstable. Otherwise, there will not be a rate, right? The very fact that 2p can make transition to 1s means that it's unstable. And hence, exists for a limited time. Which means that its energy is uncertain. And as a result, the energy of gamma from 2p to 1s also has uncertainty. Okay, so unstable states always have a uncertainty in its energy, and whatever emission they make while making the transition also has uncertainty in the energy of the pole. That's the reason why P omega T omega is not just a delta function. Why P omega is not just a delta function. But it is, of course, should be close to a delta function because this uncertainty is very small. So this is captured by what is called the Bright-Wigner formula. So let me write this down. Although we will not really need to use it very in much detail, as we'll see. P omega has the form of gamma 2p over 2 pi 1 over omega minus omega squared plus. So you can see that it's peaked around omega alpha. And typically gamma 2p is much smaller than omega alpha. Which basically means that it falls off rapidly. Away from it. Namely that when omega is exactly equal to omega alpha, you have in the denominator gamma 2p over 2 whole square, which is a large number because gamma 2p is small. But if omega, for example, is of order omega alpha, so suppose it's half omega alpha, then the denominator is like of order omega alpha square, right? And that's much larger than this one. So the actual expression for P omega is sharply peaked. Okay, so if you plot P versus omega, sharply peaked around. And because it's sharply peaked in carrying out various integrals, we can just think of the limit of omega as from minus infinity to infinity rather than from 0 to infinity, because it's beyond 0. Here it's very, very small anyway. And in fact, this formula has been written with that in mind, because you can check that integral minus infinity to infinity d omega is 1. Whereas in reality, it should have been integral 0 to infinity. P omega d omega should have been 1. Right? That means that the P omega formula that I have given here is not completely correct. Okay, there is a small correction because it's not properly normalized, okay? But it's good enough for us. But eventually, we'll see that we'll do most of the analysis without knowing what P omega is. Are there questions?
How did we get this P of omega?
Oh, this is what is called the Bright-Wigner formula. I'll not try to derive it, right? But if you look for the derivation of Bright-Wigner formula, you'll find this formula. It's basically as I said, an application of the uncertainty principle, right? You have to do it a little more carefully, but the physics of this is simply this, that because of this decay width, there's an uncertainty in energy, and that you have to translate to an uncertainty in the energy of the emitted gamma. But if you look up in a quantum mechanics book, the Wright-Wigner formula, I can find the derivation of this formula. And this is true not just for this system, right? Even for nuclear energy levels, for example, right? When there's an unstable nucleus, again, the energy of the emitted particle has a distribution of this kind. Is this okay? Yes, so if we just look at Wright-Wigner formula in quantum mechanics, you should be able to find the derivation of this formula.
Yeah, since you mentioned about the nuclear levels, when we discussed the nucleosynthesis, that time we didn't consider these subtleties, right?
No, because mostly you talked about production of stable nuclei, right? I mean, okay, we talked about production of H3, right? But this effect was very, very tiny. We didn't really need it there. Because at the end, right, H3 all decayed into He3 anyway. Right? And most of the nuclei that formed were stable nucleus, right? The hydrogen and helium. So you didn't really need to worry about this.
Here also, all that will happen from 2p to eventually some 1s state.
Yes, true. Yes, true. But in the intermediate stage, when you set up the differential equation, see the way we formulated there, we didn't really solve the differential equation, right? When we started this, you remember we used mostly equilibrium form, right? We just said that if in principle it is possible to set up the differential equation to get the result. If you did set up the differential equation, then okay, you can say you have to take into account this formula, but only for H3. Right? For other objects are stable.
Right.
Yeah. So whatever formula involves H3, we have to take that into. We do want to take that into account, but that will change the result very little because, as we saw, that the equilibrium formula itself worked quite well in that case, right? Well, we couldn't use full the equilibrium formula, right? We had this Deuteron bottleneck, but we didn't. We could get the final results to reasonable accuracy without actually having to solve the differential. Right? You have to just make sure that you wait till long enough so that Deuteron density builds up.
Okay, this is because more or less the thermal equilibrium was valid at that stage.
Exactly.
Okay.
Well, thermal equilibrium was valid, but only in a limited sense. The deuteron was in equilibrium with the bath, but before the deuteron density built up, we couldn't have used that equilibrium involving helium, right? Because the helium production had to go via deuterium.
Right, yeah.
Okay, so now this is one thing. The other thing that we need is the probability that given a photon of energy omega, what is the cross section sorry what is again one might expect that okay, if you didn't take into account the uncertainty principle, right? If these are small energies, then you would say that you need a photon of exactly the energy of the Lyman alpha photon, omega alpha, to cause this transition. But because of the uncertainty in 2p, right, you don't need exactly this energy, but you need something close to this energy, okay, of omega alpha. And that formula is given by, so this is called sigma omega. So sigma omega, it basically, you can see that it will have, by crossing symmetry, sigma omega should be related to should be related to P omega. Right? Because in one case you are talking about 2p to 1s plus gamma. In the other case, you are talking about 1s plus gamma going to 2p. Right? So clearly these two are related by crossing symmetry. And precise relation, again, I'll give the result without derivation. Okay, it's again quantum mechanics. That sigma omega will be given by 3 pi square over omega alpha square times gamma 2p. Okay, so now we can begin trying calculating the required probability P. So let's suppose that the gamma of energy omega is emitted at time t. So assuming that it survives till t prime. T prime is some time. Okay? Let's assume that it has survived up to that time. Its energy T prime is omega times lambda. Okay, these are redshift effects. So they, and here I'm using the fact that most of the energy, the main cause of energy depletion is the expansion of the universe. Okay, there is also some contribution because it can lose energy by collision with the electron gas, but that is inefficient process. And the main reason for energy depletion will be the expansion of the universe. Right? And that's what this is capturing. So then the probability that it will be absorbed between E prime plus E prime is sigma omega lambda t prime n1s. Okay, you can see the standard formula that you have been using. Cc is of course equal to 1. This is the cross section, okay? But in the argument you have to use the scaled energy. Then it's proportional to the number density of 1s because it's okay, this will be absorbed. Let me write it also by 1s to 2p prime. So because it has to hit a 1s atom, it's proportional to n1s t prime. C is the speed, right? That's the speed of light because we are talking about a photon. And this is a capture probability, the probability per unit time. So you have to multiply by dt prime to get the probability of absorption between t prime and t prime plus dt. Is this clear? So let's define q omega t prime as the probability photon of energy omega emitted at T survives till T prime. Then dq omega will be given by minus whatever appeared in the previous slide, sigma omega lambda T, right? Then 1s T prime T prime times q omega. So let me explain this. So this was the conditional probability. Assuming that it has survived till T prime, what is the probability that it will be absorbed between T prime and T prime plus dt? Right? That was this probability. Now we are talking about the actual probability. Q omega of T prime is the probability that the photon has survived till T prime. Then the fact that it will also survive till T prime plus dt prime. Right? That gets repeated by this factor, as we have seen. Okay, and you multiply by Q omega T prime because this was as for the condition probability that assuming that the photon has already survived. But if Q omega of T prime is the probability that the photon has survived till T prime, then this product is the probability that it will be absorbed between T prime and T prime plus. So then the probability that the photon survives till dt prime will be given by the original Q omega minus this, right? And that's this. Is this clear? Okay, so this is telling us the rate at which the photon survival probability decreases as a function of time T prime. The more time you spend, the more likely that the photon would have gotten absorbed by some 1s on the way.
This dt prime will not be there in the RHS, right?
Thank you. Yes. So dq omega T prime would have been that. So you can integrate this. Boundary condition is that Q omega T should be 1, right? Because that's when you started, right? Of course, the photon was produced at time T. So this gives us that Q omega at infinity. Why am I calculating infinity? Because you want to see calculate the probability that the photon survives all the way, right? So that it doesn't excite a 1s back to 2. Right? That's what you want to do, right? That T will be roughly this, right? That the photon once emitted should not excite 1s to 2. So Q omega of infinity will be given by exponential minus integral T to infinity sigma omega lambda T, right? Is this clear? If you integrate this equation, right? This is d prime of log of Q omega of T prime, right? So you can integrate it from T prime from T to infinity. That gives you the difference between log of Q omega at infinity minus log of Q omega at 1 at T. Right? Log of Q omega of T is 0 because Q omega T is 1. So you get log of Q omega T by integral of this and then use this exponential. Are there questions? Let me write this formula once. So what we are going to do now is to
It
change
is
value.
lambda of t by t prime.
Pardon?
It is lambda of t divided by lambda of t prime.
Lambda of t over t. Now we change variable. From t prime to omega prime, which is omega lambda of t over lambda of t. So this will tell us that t omega prime is given by omega lambda of t over lambda of t prime squared times lambda dot of t. Right? Which is minus omega lambda of t prime times h of t prime. Because lambda dot over lambda is h. And this is of course omega. So using this, we can write t omega of infinity as exponential minus integral. Okay, this minus sign means that the integration limits will be reversed. So you see that as t prime goes to infinity, right, this goes to 0. Because lambda t prime, of course, goes to infinity. So this will be from 0, and as t prime equal to t, this is just omega. So 0 to omega, t omega prime, sigma omega prime, n1s. Okay, I'll just write it as t prime because t prime is whatever it is corresponding to omega prime, and divided by omega prime h of t. Right? Because when you convert from the okay, when you convert from dt prime to d omega prime, you get this omega prime h of t prime. Is this clear? So I'm going to write this formula once more because you'll manipulate this. So q omega is exponential minus integral. Now sigma omega prime, let me remind you, was 3 pi square gamma 2p over omega alpha square p omega prime. And you don't need to know too much about p omega prime except that this is sharply peaked. So this basically means that what you have here is one of these factors here in sigma, the p omega prime factor, is sharply peaked around omega alpha. The other quantities are slowly varying functions of omega because these are just cosmological evolution. So you can approximate this essentially by pulling out the slowly varying factors. So let me write this, then explain this. So p omega of infinity you can approximate by exponential minus pi square comma 2p n1s t infinity. Okay, so let me explain what this is saying. You see, what this is saying is that P omega prime is sharply peaked around omega prime equal to omega.
Ashok, the integration was from 0 to omega.
From 0 to omega. Thank you.
Why it is from omega to infinity?
It does from omega to infinity.
No, at t the frequency will be omega. At infinity it will be 0.
Yeah, t prime
Okay.
equal to infinity, this will be 0, right? Yeah, so I think this is 0 to omega. So what we did here, okay, this of course is a constant. Here, what I used is the following, that this one will be sharply peaked around omega prime equal to omega. And similarly, because this integral is from 0 to omega, right? Here you say that we start with a photon of energy omega, but essentially this omega is being produced from a 2p to 1x, right? So that will be also close to omega. We started with omega, which is close to omega alpha, and then you are trying to ask that what is the probability that it will survive for a certain time. Now, because you are starting close to omega alpha, this one decays rapidly. It decreases rapidly as omega prime becomes larger, which means that most of the contribution to this integral is going to come from the omega prime equal to omega alpha. That means more or less immediately after it has been produced. Because if you wait till too long, so the physics is the following, that if you wait too long, then the energy will get depleted so that it cannot produce back a 1s to 2p transition anymore. So whatever is happening, this absorption probability gets most of its contribution from time period immediately after its production, so that it doesn't lose too much energy. And because of this rapid fall as a function of omega prime, right? We saw that the width is about omega, controlled by gamma 2. Because of this rapid fall, this is a rapidly varying function. That means that for these quantities, we can essentially use the values at the time of production, because most of the absorption is going to happen close to the time of production. So that's the reason why I have pulled out this n1s over omega prime ht prime as the n1s of t times omega alpha h. Is this argument clear? So you're using the fact that this is a rapidly varying function of omega prime to say that the things which are slowly varying, we'll just treat them as constant and we'll pull them out of the integral. So this quantity is what we'll call x.
But I understood about this taking out n1s and gamma 2p, etc. But what about h of t?
H of t is also slowly varying function, right? Because it's the expansion of the universe, right?
Mm-hmm. Okay.
So compared to the microscopic scale, see, the gamma 2p is really tiny value, right? Because I mean, it's small compared to omega. So this is falling off very rapidly, okay, this quantity. And during that time, right, H of t doesn't change very much.
Yeah, okay.
So it's like if you produce a photon, right, and if it loses 1% of the energy, already it becomes inefficient to produce back from a 1s to 2p transition. Right, and 1% means 1% change in H, right? Because the photon frequency basically falls as in terms of as 1 over lambda. Okay, so now there is only one more step, so let me write it. So then the P remember was the total probability that the photon will not excite. So this calculation is the probability that a photon of energy omega would not produce back a 1s2p transition. So the probability that a Lyman alpha photon produced from 2p to 1s will not produce back a 1s2p transition is integral d omega 0 to infinity integral d omega p omega times p omega of infinity. Because this is the probability that the Lyman alpha photon carries between energy omega and omega plus d omega. Right? So you have to multiply this by that probability and integrate. Is this clear? This, now you can put back the expression for p omega of infinity, and if you change variable, so choose variable y as integral with this choice of variable, this becomes integral 0 to infinity 0 to 1. Is this clear? This is exponential minus x times y, right? This is by definition or y. And the only other thing I'm using is that dy, we are changing variable from omega to y. So dy is basically p omega d omega, right? So this whole p omega d omega I can write as dy. And then the range of integration, when omega is 0, y is 0. And when omega is infinity, then from 0 to infinity, p omega d omega should be 1. Because that's the total probability. And that's why I'm writing it from 0 to 1. So this is 1 over x times 1 minus where x is given here. So this is what leads to the final formula for P. So next time we'll calculate the similar formula for P bar, and then we'll be done with, that will determine all the quantities that appears in a differential equation, and then we can substitute on it. Okay, so I think I'll stop here. Are there questions? Okay, so if there are no questions, we'll meet tomorrow. So tomorrow, of course, there will be regular class. So tomorrow's class will be regular lecture.
Thank you, Ashok.